Welcome to the Mac Biophotonics FLIM module. FLIM, or fluorescence lifetime imaging microscopy, is a method of measuring fret that utilizes the lifetime of the donor fluorophore. There's two ways of measuring fluorescence lifetime, in the time domain and the frequency domain. This module will cover doing FLIM in the time domain using time-correlated single photon counting. Now, setting up the scope is a lot the same as for the SP5, so with these two monitors. But additionally, 10 minutes or 15 minutes before you get started, you're going to want to turn on the MP laser from a standby to on. And it'll show that the power's ramping up, and it takes about 15 minutes to do so. Now, we've already done this, and we're already pulsing and ready to go. In the actual LAS advanced fluorescence software, there's a number of things that you need to turn on. If you go to the configurations tab at the top left, we're going to go ahead and turn on our MP or multiphoton laser by clicking this box here. Now, if you go back to the Acquire tab, what we're going to do is we're going to change our format, our pixel format, from the typical 512 to 512 down to 256 by 256. The reason for that is that pixel array will correspond to the pixel array in the acquisition software for the fluorescence lifetime imaging microscopy. Another thing is we're going to click this pinhole. Now, multiphoton lasers generate confocality through the angle at which they intersect and don't actually require pinholes. So what I'm doing here is selecting the pinhole, and it'll actually open it to the maximum of 600 microns on this tab here. Subsequently, you will go to the load single settings, and you'll scan down, and depending on what fluorophore you're using, in our case we're going to be using CFP variant M cerulean, you can scan down all the way to these MP settings. They have MP at the front, and you select whatever you want. We're going to select MP CFP because that corresponds to the fluorophore we're using. Another thing you're going to want to do is actually click this MP tab at the top. This means that the light path is going to go through the MP laser. At the bottom here, where it actually has an underlined MP laser, you can click that, and this gives you a number of settings on the MP laser where you can adjust the wavelength. So the beauty of this multiphoton laser system is it's a tunable laser, giving you a wide range of wavelengths that you can excite. For our uses, we're going to use 820 nanometers, but I encourage you to look up the appropriate wavelength for the fluorophore of interest. Once that's done, there's this interlock here that you'll have to click 1, 2, 3 to turn on, and you'll actually hear the displacement of the shutter there. So once that's done, we're going to turn this off. And if we've done everything correctly, the MP CFP setting will show us the emission spectrum of the CFP. And so we're going to set our PMTs up to do FLIM. PMTs 1 and 3 are the PMTs assigned to do FLIM. So we're going to use PMT for 1 to start. We're going to select FLIM here. And we've also selected a lookup table, the P color 3. I encourage that one, and I'll show you why in a minute. With that, there's a number of settings here. So this is the filter wheel. This is essentially the power. You never want this value to go up above 12.5%. If you go to 25 or anything higher, you risk bleaching your system or your cells and affecting the lifetime. So with that, we can also adjust the range at which we're acquiring photons. So for this particular one, we have it from 450 nanometers to 515 nanometers, and that should be good for our uses. So with that, we can go live and see if if our system is set up properly to acquire photons from M cerulean. So when we start scanning here, you can see that we have 2 cells, and we can adjust the Z position. Now, this lookup table is set up as such that if your intensity is on the low end, your pixels will show up with a green pseudo color, whereas if your power increases, then you'll go into the light blue, blue, and etc., depending on the lookup table. So we like to keep our lookup table color around the green, and this tells us that we're probably not bleaching our fluorophore at this power. Although I won't show you with this, but if you turned up the power on the FW that I was just discussing, you'll see that the color starts to raise to the blues, the pinks, the reds, and then up to the yellows, which will definitely be bleaching your fluorophore. So now that we know that our scan is working, we're going to go ahead and move over to our other computer here, which we'll call our FLIM computer, and turn on 2 softwares. The first software will be our acquisition software. So the pixel array that I was discussing earlier, the 256 by 256, corresponds to this 256 in the Y and 256 pixels in the X. And so they have to be exactly the same, or else you'll see the image will be skewed off to one direction or the other. Now we want to load a setting here for our particular uses, and we'll go to main and load predefined setups. Actually, we're going to go to load. Here in file format, we'll go down to SPC setup, which will bring up this MBF underscore 256 underscore 256 dash set. And we'll select that file and load it. Once we've done that, you should see the setting show up at the top of the acquisition software. The other software is actually the analysis software. So if you double click on it here, it'll open up here. So with those 2 softwares open, we're going to go ahead and acquire an image, and I'll take you through the acquisition all the way to the analysis of the image. So if we begin to go live, time domain FLIM relies on the acquisition of photons, and from that it generates decay curves. So to collect enough photons, we need to collect over a period of time. For our uses, we're going to use 60 seconds, and you can adjust this down here at the bottom in the acquisition software to any number you like. If you have a really dim fluorophore, you would consider increasing the collection time, whereas with something very bright, you could probably do with a lot less. And another thing you'll notice, so I'm going to stop the scan just quickly here, is that these values here, the CFD, the TAC, and the ADC, for standard users, you don't really need to know too much about it. But what you should see when you turn on the scan is these values actually go up to 1 to the exponential 4. And so you know you're acquiring photons. And so what we'll do, now that we have a bright enough sample here, is we're going to start acquisition. And this will be a 60-second period, as I was saying, as we're acquiring photons to generate a decay curve. Okay, now that our 60-second collection time has elapsed, you see that we can stop the scan. And if you look here, you'll see a mirror image of our cell that we've acquired here in the acquisition software. The red corresponds to a higher number of photons at that particular area, whereas the green represents less photons. So what we're going to do is we're going to send this image over to our analysis software to generate a decay curve and to actually calculate the lifetime in the cell. So what you'll do is you'll go to main, and you'll go down to send data to SPC image. And so what you'll see is this image will show up in the analysis software but in fact 180 degrees rotated. This is just the consequence of the software. Once in the analysis software, we have settings that are optimal to generate reliable decay curves. And so what you can do is just press this button down here, which is an arrow, which will refer back to the original default settings. So if you press this, load default fit conditions, and you'll click yes. And what you'll see down here, right here, is the actual decay curve. So within this blue crosshair, it's selected a single pixel. And at that single pixel, we've collected 9,308 photons, which has allowed us to generate this decay curve. Now over here gives us an actual absolute lifetime value. For this particular fluorophore, which is a CFP variant, is around 3.9 nanoseconds. And you can actually drag this crosshair around to different pixels on your image to get absolute lifetime values. And you'll see that the decay curve at every pixel changes slightly. From that, we want to actually generate what we're going to be using in our publication, our actual lifetime image, a photon-weighted lifetime image. What we have here is just an intensity-based image. So to generate the intensity-based lifetime image, we'll go to Calculate, and we're going to click Improve Matrix, the second option. Now, depending on the size of your image, if you've zoomed in or you're fully zoomed out, this will determine how long this process of calculating takes. Typically, it's on the order of 30 seconds, but again, if you're dealing with a large, unzoomed in frame, then this typically takes longer. And so what you end up with is this lifetime value here. On the right is this histogram, which we don't see yet because we haven't adjusted our values. But what this will represent is a histogram where the lookup table corresponds to the lifetime values in the histogram. So if we want to adjust the range of the histogram, so depending on what fluorophore you're using, for this M turquoise, we would ideally like to look within the range of 3,000 to 4,000 picoseconds, or 3 to 4 nanoseconds. To do that, we go to Options, we go to Color. Within Color, it gives us this, if we want to set a continuous range, it gives us the option of actually setting our range of lifetimes that we want to visualize. So as I just said, for our particular fluorophore, we'd like to look between 3,000 and 4,000 picoseconds. For some reason, all the settings are in picoseconds. If you're used to thinking about it in nanoseconds, then do some math in your head. So once I click that and I set the range to 3,000 to 4,000 picoseconds, you'll see that the color of my lifetime image changes. And you'll see that this range that we set is very squashed. You can actually spread that out by pressing this button right there. Okay, and as you see now, this is the histogram I was describing, where on the y-axis we have the number of pixels, and on the x-axis we have the lifetime of those pixels. And we can see that the mode lifetime, i.e. the lifetime that is most represented, is roughly around 3.8 nanoseconds, right here at the highest, at the peak of our histogram. So what we have here is a histogram that represents the lifetime of our cells. Since this fluorophore, our donor fluorophore, is M turquoise, we'd expect a natural lifetime of around 3.8 to 4 nanoseconds. And in fact, what we did get, so here when we look at the mode lifetime, we get a lifetime of around 3.8 nanoseconds, which corresponds with the natural lifetime of the fluorophore. So as I mentioned, this first panel on the left is a photon-weighted image. So this is essentially just the collection of photons, an intensity-based image based on our acquisition. This panel over here is a lifetime image. This color does not represent fluorescence, but is actually a pseudo-color to correspond to this range of lifetimes in this histogram. And this rainbow lookup table ranges from low lifetimes in the red to high lifetimes in the blue. To actually export the data and to do further analysis and to generate publication quality images, what we're going to do is we're going to go to File. We're going to scroll down to Export. And what we're going to do is it gives you a number of options of things to export. We're going to export the T1, which corresponds to the lifetime, the chi, which corresponds to our numbers in our decay curve down here, and the actual photon numbers. So these three, the T1, the chi, and the photon numbers, are the three files that you need to export in order to properly analyze the data. So once you press Export, you can save in a setting. I'm in the truant settings here under my name, Nick. And I'll save this for February 10th. And this is just the control, so I'm going to label it as such. And that'll save the three things that I just described. However, if you want to be able to come back onto this computer and visualize this exact image in case you wanted to change the lookup table, say you wanted to change the range on which you're actually looking, so say I wanted to come back and change the range of actual lifetimes being displayed in my histogram, then you actually need to save this file here. And to do that, you go to File, and this is just File Save As. And so I will also save this as Control 1, so I know it corresponds with the chi, the T1, and the photon numbers from Control Experiment 1. So when choosing the right fret pair for your FLIM experiments, it's important to consider a number of factors. We like using M-cerulean because of its mono-exponential decay curve. Other fluorophores have multi-exponential decay curves, which are more difficult to interpret. Fluorophores such as Venus for the yellow. When setting up a FLIM experiment, you want to have a minimum of 4 controls. The first control is your donor alone. So this is to determine the natural lifetime of your fluorophore and to see if it corresponds with what's in the literature. Your second control is your donor fluorophore fused to your gene of interest. The third control is your donor fluorophore fused to your gene of interest plus just your acceptor alone. Your fourth control, which is often the most difficult to find, is a positive control, where you'd expect to see a decrease in the lifetime relative to your negative controls, the first three that I described. And your fifth experiment will actually be your test dishes. So every time you come in here to do a FLIM experiment, it's important to have at least 3 of the controls that I described. Now that we've acquired our control image, we'll go ahead and acquire our test image. For this particular experiment, we have our donor, M turquoise, fused to an ER marker, and our acceptor, in this case YFP, fused to a mitochondrial marker. So now that we've got our sample in focus, everything is done the same, we'll go ahead and go live. We see that the intensity of our pixels corresponds to the green as I described, and we shouldn't be getting any bleaching occurring here. Once we feel comfortable with our field of view, we'll go over here once again and press Start. Well, we have a 60-second acquisition time. Following 60 seconds of acquisition, we'll stop our scan here. And as you see, we've acquired our cell. And once again, we're going to go ahead and send this to to our analysis program. Once again, I'm going to restore the default settings and click yes. And you'll see what will happen is the decay curve will change slightly depending on the settings that you have. And once again, we will improve the matrix to generate the lifetime image. Now, since we're looking at fret between the mitochondria and the ER, we wouldn't expect the lifetime to change all throughout the cell, only perhaps where these two organelles are interacting or coming into close spatial proximity. So that'll be a really good control for our particular case to know if we're actually seeing legitimate fret versus just fret due to bleaching or random collisions. Following improving our matrix, once again we're going to adjust our scale by clicking on options and going to color. As I mentioned, for M turquoise, we'd be expecting a range of photon or of lifetimes between 3,000 and 4,000 picoseconds. So we will adjust our range to correspond to those values. What you see is a heterogeneous distribution of lifetimes throughout the cell, which likely corresponds to fret between the ER and the mitochondria. I'll show you how to save this one more time. So again, we're going to export our T1, our chi, and our photon number. And since this is a test plate, save it as such. And once again, if you actually want to save this particular experiment and be able to come back into the software and adjust range values, then you could do so by pressing File, Save As, and I save this as Test 1, which will correspond to the T1, chi, and photon number values. In a separate module, we'll show you how to actually take these lifetime values and actually quantify them and generate graphs that could be used in publications. To ensure that you have both your donor and acceptor, it's often required that you take an image, a fluorescent image of both your donor and acceptor, in this case M turquoise and YFP. So to do that, you can jump between the argon laser and the multiphoton laser. So you actually get a fluorescence image of both your donor and acceptor as well as your lifetime image to show that you actually have the fluorophore and both of the fluorophores in the cell. To do that, I'm just going to load up a sequential setting, as was covered in a previous module to do multi-channel imaging. I'm going to load a sequential setting for CFP and YFP. Now, you'll remember that we're a 256 by 256 pixel array, which is relatively low resolution. If you want to step up the pixel array just for your fluorescence images, this is acceptable, but you'll have to make sure to turn it back down to 256 by 256 when you're going to acquire your FLIM image. So for this particular case, we'll move it up to 512 by 512. And so our first scan should get, let's just make sure that our CFP is bright enough. And we see that it is indeed. So we'll turn down the gain on that a little bit. And then our second scan should see our acceptor, YFP, which it does, the mitochondrial marker. So what we can actually do is start and do a sequential a sequential scan for both our donor and our acceptor. And what you'll see is now we have our fluorescent image, donor, acceptor, as well as our lifetime image, all of which you can include in a publication panel showing lifetime values.